Welcome to David Alexander Maths Tuition. This is chapter 12b on finding the derivative from first principles. So here we have a curve, and one thing we know about a curve is that the gradient is constantly changing. The gradient of the curve at any particular point is the same as the gradient of the tangent at that particular point. So if I select x equaling 1, so what is the gradient of when x is 1 on this curve? Well, it's the gradient of the tangent at this point. So I can draw in a tangent and work out the gradient, or work out an estimate of the gradient on the curve by doing change in y divided by the change in x. But for that I need to draw a perfect tangent, and that's clearly quite challenging to do. Now if I were to add if I were to draw a chord, let's say where x is 3, then we can see that y is 9. So by the way, this is the y equals x squared. If I were to draw a chord from here to that point there, what is the gradient of that chord? Well, again, I can work it out changing y over changing x. Now we can see that this chord is much steeper than the tangent, so the gradient will be greater. But it might not be a million miles off. But what if I slid this point a lot further down, say to where x is 2, and drew a chord from here to here? Again, can't see it particularly well there, but we can see that that is less steep than the chord that I drew before, and it's still steeper than the tangent, but it's sort of heading in the right direction. Now what if I slid this point really close, so say to this point here, so the chord that I'm drawing here has a gradient that is getting pretty close to the gradient of the tangent. So the closer this point is, in other words, when I add on only a tiny amount to my original x value, then I'm getting closer and closer to the gradient of the tangent at that point. So what we are doing here is we're suggesting that if we just add an infinitesimally small amount to our x value, then we will have an infinitesimally short chord, which will then have exactly the same gradient as the gradient of the tangent at that point. So as I mentioned, this is the curve of y equals x squared. So when I've got an x value of, let's say, x, then my y value will be x squared. Now what if I add something onto x? Let's say I'm adding h onto x. So the x value will be x plus h, and then my y value will be the x value squared. Well, if the x value is x plus h, then the y value will be x plus h squared. So what is the gradient of the chord if I'm using the coordinates x squared and x plus h squared? And remember that this plus h that I'm adding on, that was that infinitesimally small amount that we were talking about. So the gradient again is just changing y over changing x, so it's going to be x plus h all squared, take away x squared, over x plus h take away x. So those x's on the bottom will cancel. Expand the brackets on the top, I'm going to get x squared plus 2xh plus h squared take away x squared all over h. These x squareds cancel, and if I divide through by h, then I will get 2x plus h. Now remember, we were saying that h was infinitesimally small, so if h is tending to 0, and this is how we would express it, then the gradient will be simply 2x. Okay, so at the point where x is 1, the gradient would be 2 times x, 2. Where x is 3, the gradient would be 6. And this 2x, this is what we call the derivative, and we can write this as dy by dx. So that's what this d means is just a tiny change in y over a tiny change in x. So dy by dx is 2x, or sometimes you'll see it written as f dash x, which is 2x. So this is for y equals x squared, 2x. This is the formula we use to calculate the gradient at any particular point. Okay, so just one final thing I want to mention. So here we have x, and this is the function of x. Here we've got x plus h, and this is the function of x plus h. So to this is the formula we use when we're trying to find the derivative from first principles. It's the f of x plus h minus, so change in y, so f, the function of x plus h minus the f of x, over the change in x, which is x plus h minus x, and of course the x's cancel out as we've seen before. So this is the formula we use to work out the derivative from first principles, the function of x plus h minus the function of x all over h. Show from first principles that the derivative of 5x squared is 10x. Okay, so we know that the function of x is 5x squared. So our derivative, we'll write that as f dash x equals, and we need to remember that this is as h, that this tiny value that we're adding on is tending towards 0. And remember that it's the f of x plus h minus the f of x all over h. So what is that as h tends to 0? So our function is 5x squared, so we're going to be subtracting 5x squared. Now if I'm adding h to 5x squared, then that would be 5 lots of x plus h squared. So that's 5 lots of, in brackets, x plus h squared, and that is going to be over h. Okay, so let's keep going. Let's expand the brackets. So that's going to be 5 lots of x squared plus 2xh plus h squared minus 5x squared over h. And again, as h is tending to 0, again we're just doing algebra here really, nothing else going on, just expanding those brackets. 5x squared plus 10xh plus 5h squared minus 5x squared over h. So this is always what happens. This will cancel with that. Now let me just take the workings up here. So again, as h is tending to 0, we are left with just h will cancel out with that h and one of those h's, so that will be 10x plus 5h. Okay, now as h tends to 0, 5h tends to 0. So therefore the derivative of 5x squared is 10x, because this part here is 0. Show from first principles that the derivative of 2x cubed is 6x squared. So the function of x is 2x cubed. So the derivative is going to be, as h tends to 0, it's going to be the function of x plus h minus the function of x all over h. Okay, so what we've got here is the function of x is 2x cubed. So if I'm adding on an h to my x value, then that is going to be 2 lots of x plus h cubed. So 2 brackets x plus h cubed, and all of this will be, of course, still over h. So expand out the x plus h cubed, and let's just do that over here. So x plus h, x plus h, x plus h, so that's an x squared plus 2xh plus h squared, multiply through by x cubed plus 2x squared h plus h squared x, now multiply through by h, so h times, so that's going to be plus x squared h plus 2xh squared plus h cubed, so that should give me 1x cubed. So remember that an x squared h is the same as an hx squared, so there's 3 there, plus 3x squared h plus 3xh squared plus h cubed. Okay, and then it's 2 lots of all of that, so I'll just write that in, but double it all. So that's 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed minus 2x cubed all over h. So the 2x cubed minus 2x cubed can go, and we can just divide through now by h, and that's going to be 6x squared plus 6xh plus 2h squared. Okay, so what we can say now is that as h tends to 0, 6xh will tend to 0 and 2h squared will tend to 0. So if this is 0 and this is 0, then we can say that our derivative is 6x squared, which is what we're aiming for.